The next talk will be was announced, and Nikolai Krivulin from Следите.
Yeah. Thank you, Nikolai, for the introduction. Let me start my presentation. I will talk about a real-world application of tropical algebra. The application area is just project scheduling. It's one of the most popular application area for demonstrating the ability of tropical algebra to solve real-world problems. Let me start with some outline of the presentation. First of all, I would like to present the motivating or motivational problem from which comes from project scheduling. Next, I will present a brief overview or outline of the tropical mathematics ideas, notations, and other points which we will use later when solving the problem. And the last part of the presentation is just a description of the solution process of the problem and the presentation of the results. Let's talk about the application problem. Imagine that we have a project which consists of a set of activities which have to be performed in parallel. There are some constraints imposed on the start and finish times of the activities. These are release times, deadlines, start and start-finish relationships. Relationships between start and finish times of activities. The release times define the earliest time for activities for each activity to start. The deadline is latest time for each activity to finish, and the start and start-finish relationships give us time minimum allowed time lags between start of one activity and start of another activity, if we are talking about start-start relationship, and between start of one activity and finish of another activity for start-finish constraints. Now we have to discuss the scheduling objective, the optimality criterion which we use to solve our problem. As the optimality criterion in this problem, we take the maximum deviation of start times, which we have to minimize. The minimum deviation of start times over all activities. And we have to minimize this deviation, and this problem corresponds to the situation when we try to make our activities to start at the common time as far as possible, as much as possible. Now we have to introduce some notation to make a formal representation of the problem. X, Y, and Y, I are the unknown start and finish time of activity I. G, I, and F, I are the given release time and deadline for activity I. And B, I, J, and C, I, J are given lags for start, finish constraints. Just to represent in a formal way our constraints, we have to as a formal representation of our constraints, we can write these inequalities. The first two inequalities are obvious, and the last and the second inequality in this line is also quite understandable. And we have to represent the idea that the time the start time of activity I is not earlier than the start time of other activities j plus the lag bij, and we have to make all these constraints satisfied, and because of that we combine them using the max operator. This is a second kind of constraints which come from start-finish relationships, and we can exclude just yi, the finish time of activity I, from our consideration by combining this inequality with this constraint with the deadline. And after that, we, for our purposes, for our problem, it is enough for us to take into account just this constraint. The last step is just the formulation or definition of the objective function in our problem, which is a core thing of our optimality criterion. This is just the maximum deviation of start time of activities. This is an obvious, obvious expression, and please look at this modification of this part. You understand that I think that you understand that we try to represent all mathematical all mathematics is in our problem just using max operator, just to exploit later max plus algebra or tropical algebra. Finally, we can combine our constraints with this objective function into one problem of this kind, of this form. It is easy to see that this problem can be reformulated as a linear program and then solve it using numerical algorithms or numerical schemes or numerical procedures from linear programming. It is good for us, but this approach cannot allow us, cannot provide an analytical solution of the problem, and moreover, following this approach, I mean linear programming approach, we cannot obtain a complete solution of the problem in analytical form, because, for instance, simplex algorithm gives us only one numerical solution of the problem. And that will be our aim, our purpose, just to provide or to derive an analytical solution for this problem. For this purpose, we reformulate this problem in tropical mathematics sense or in the tropical mathematics setting, and then solve the problem using results and methods of tropical optimization. Let us talk about tropical mathematics and tropical optimization. Tropical or idempotent mathematics is the mathematics of algebraic systems with idempotent operations. An operation is idempotent if applied, a binary operation is idempotent if applied to two operands of the same value. It produces this value as output. For instance, specifically, for instance, the max operation is we can consider it as a binary operation. It is an idempotent operation. Tropical optimization uses models and methods of tropical mathematics to formulate and to solve optimization problems. Actually, I would like to say that today there are many applications of tropical optimization known in the literature, but historically the first applications came from project scheduling. There are applications in the area of location analysis, location problems. There are applications in the classical application in the area of transportation network. There are a new area of applications in the decision-making problems and some other applications. the most probably popular instance of tropical algebraic systems is a max plus algebra. Max plus algebra is a set of reals with minus infinity adjoint, which is closed under two operations, addition and multiplication. Addition is defined as maximum and multiplication as arithmetic addition. And with respect to addition, we have a natural element 0, which is denoted by this specific symbol. And when we are talking about maximum as the addition, we have minus infinity as the natural element with respect to this addition. And with respect to this specific multiplication, which is actually the arithmetic addition, we have a natural element 1, which is actually arithmetic 0. Yeah? Let me put the max plus algebra into the more broad context in the context of general idempotent semifield, because the later results, which we will present, they work for general semifield, not only for max plus algebra. There are many other examples of idempotent semifields. For instance, a semifield max algebra, so-called max algebra. This is a semifield where addition is denoted as addition is defined as maximum, and multiplication is defined as usual. There are other examples, but to have a general approach to handle the problems, we will talk about a general idempotent semifield. This is a system with of a carrier set x, capital X, with two operations called addition and multiplication, and with two natural elements with respect to addition and multiplication. The main point is that the addition is idempotent, and the multiplication is invertible. I would like to say that the general theory of the general tropical mathematics deals with idempotent semi-rings, where multiplication is not obviously invertible. But we consider just idempotent semifields. This term comes from the invertibility of multiplication. We also assume that rational powers are well defined in our algebra, and it is interesting to note that the tropical analog of of an equality for geometric and arithmetic means looks like this one. You can also see what is the inverse in terms of the max plus algebra. Right? In terms of the max plus algebra, where addition is multiplication is arithmetic addition, the inverse is just the opposite number. And the same comment we can say about make about powers in max plus algebra. In max plus algebra, the powers corresponds to arithmetic products, and because of that, we have all powers with any exponents well defined. We can extend our scalar algebra, our scalar idempotent semifield, to a system of vectors over the idempotent semifield and matrices. Actually, vector and matrix operations are performed using the same rule as in ordinary mathematics, but with scalar arithmetic addition and multiplication replaced by new addition and multiplication. This is an example, for instance. I would like to note that we do not use the multiplication symbol as it is usual in algebra, just to save writing. We will use the term regular vector. Regular vector is a vector without zero components. We also use, to describe some elements of our problem, we will use the vector of ones. In max plus algebra, this is a vector of arithmetic zeros, because this one is the natural element with respect to multiplication, but multiplication in max plus algebra is defined as addition, and because of that, the natural elements with respect to multiplication is just zeros, arithmetic zeros. Just to be able to represent our expression in a compact vector form, we introduce this operator, a multiplicative conjugate transposition of a vector. If we have a column vector, conjugate transpose of this vector is a vector which is obtained by transposition of the original vector and by replacement of each entry by its multiplicative inverse. Finally, we will use this notation to represent the tropical analog of vector norm. It is easy to see that we can, for instance, in max plus algebra, we can use this representation of the norm are quite natural, and actually the vector norm is tropical algebra is simply a maximal element, the maximum element of the vector. I mean max plus algebra, I mean algebra where addition is defined as maximum. This slide demonstrates the same tricks with matrices. The only thing I would like to mention or to note is this definition for the matrix norm or for a matrix norm. This is a tropical analog of a matrix norm, and we will also use the term column regular matrix to describe a matrix, to describe matrices which have no zero columns. For square matrices, we can introduce a little bit more ideas or notions or notations. For instance, we can use the identity matrix, which looks like an ordinary one, but we have to replace ordinary zeros and ones by tropical zeros and ones. Positive integer powers are defined routinely. They indicate they indicate iterative multiplication of a matrix by itself, but we mean here the tropical matrix multiplication. You can see the formula which is used to represent the tropical trace, which is quite natural, and it is easy to see that this tropical trace possesses the same properties as this ordinary trace. This is the last slide, which presents some advanced notions, some advanced ideas relevant to square matrices. First of all, we define this function of this function, which is calculated, which can be calculated for any square matrix as a sum of traces of matrix powers, and this function can play the role of matrix determinant. This is a well-known Kleene star of a matrix, which is the sum of these powers of the matrix. And this is a definition for the spectral radius of a matrix in tropical algebra. And in fact, this tropical radius is one of the eigenvalues of the matrix in tropical algebra. But these details are not important for us now. Let us revisit our ordinary representation of optimization problem, minimax optimization problem to solve. We have got this representation. Now we have to, the first step to solve this problem is just to rewrite, to represent this problem in terms of tropical mathematics. Moreover, this is a scalar representation, but we would like to have a vector representation. To this end, we introduce matrices and the vectors corresponding, corresponding matrices and vectors. And after that, it is easy to see that each element of this description can be translated into these elements, which are used. Tropical algebra or matrix operations from tropical algebra. Now we have to solve this problem. To do that, first we have to note that this problem is a special case of this problem, but this problem has a known solution, and our problem is just to adapt the solution known for this problem to this problem. And after this adaptation, we obtain some possibilities to reduce the solution of the original problem considerably. Let us look at the general problem, which is the base for our solution. This problem looks like this one. You can see that it looks like a linear program. However, the objective function is not linear here because of this operator. But the representation is quite compact of the problem, and to represent or to describe the solution of this problem, we add or introduce these symbols to represent these big or complex sums of vectors. With these symbols, we can formulate the solution of the problem in the form of this theorem. We can see the problem once again in the first line, and next you can see the solution. And first of all, there are some assumptions which we have to provide. The interpretation of assumptions are quite natural. For instance, this assumption provides us with the possibility to solve this inequality, to have a non-trivial solution of this inequality. And this assumption is to be sure that all these inequalities have a non-trivial solution. Now we can look at the solution. The minimum in the problem is represented as this sum of using this expression, and all regular solution can be represented in parametric form. U here is a vector u is a vector of parameter here, and other elements of this representation you know what they can mean. If we apply the previous solution to our problem with a reduced objective function, we arrive at the solution in this form. The solution, as you can see, the solution, this solution looks easier than the previous solution of the general problem. How many minutes? Maybe 3. Yeah, I will try. And actually, the idea to obtain a simplified solution for the problem of interest is based on substitution, of course, our new matrix for the matrix A, and after that we can represent the overall solution of the problem in this form, and the main idea is just to use the inequality between geometric and arithmetic means, which allows us to reduce the number of summands in the big sums to 1 or 2. And if we do that, we can see that this guy is equal to this expression. But this is a first part in the expression for the minimum of the objective function. This is the second part in the sum, which describes the minimum of the objective function. It takes this form, and we can use the inequality of between geometric and arithmetic means once again to get finally this result. Actually, the minimum of the objective function theta is calculated in this form, which is more easy than original form. Once again, we can use the inequality between geometric and arithmetic means to simplify the expression which represent all solutions. First of all, to simplify this matrix, this Kleene star matrix. This slide demonstrates or presents the solution once again. The last slides demonstrate a numerical example. For instance, for the matrix for the problem of the dimension 4, we can define our matrices and vectors in such a way. After that, we can use our formula to calculate the minimum of the objective function theta. We have 2. After that, we can calculate the matrix G, which is used instead of Kleene star in the final expression. Finally, we have the solution in this way, in this form, and this is a matrix which generates solutions. Its columns generate the solution. We can see that these columns are collinear in max plus algebra sense, and using this fact, we can simplify. We can take only one column of the matrix and have the solution written in this way. And the last line shows how the solution looks like in scalar way, scalar form. Yeah. This is the last slide. Thank you for your attention.
Thank you.
Thank you.
Questions? Maybe some comments. But I think that you have to.
No, can you say that it's new implementation of the theory of topical theory, because unknown application, yes?
Moreover, this is an unknown application of existing results in tropical optimization.
Can be possible to obtain the new application.
Yeah. Actually, this is a new formulation of project scheduling problem. This problem did not solved before, and the theory is an application of known results in tropical optimization. These are new applications to some extent.
Thank you.
In both.
The theory of optimization theory is a very, very good field for applications of tropical algebra, because we heard that from this talk that a lot of such kind of problem could be solved by simplex methods and by linear programming algorithms, but actually the tropical algebra give us another language to solve this problem, another language to construct the algorithms and so on.
No, not algorithm, to provide us with analytical solution.
Yes.
Linear
Computation in tropical semi-field gives us
analytical solution.
Algorithm. But this kind of algorithm is such kind computation in closed form, but in tropical.
Yeah.
Okay, I think that. Okay.
Can I ask a question, please? So I wonder. So please excuse me if I ask a very stupid.
Yeah, probably.
Okay, so you like that. Do there exist optimization scheduling problems with so-called NV-free optimization problems?
Which problem?
So there exists a series of problems which are called NV-free.
What is NV-free? Oh, I don't know what is that. I only.
I know a little bit about that. They also in this one.
I'm sorry, I cannot comment on this specific kind of problem. But I would like to say that, of course, this is not a most powerful approach to solve scheduling problems, and moreover, this approach is applicable and can be applied for time-constrained problems. Only for time-constrained problems. If we would like to take into account other constraints like finance or manpower, I'm afraid that you will fail using tropical approach. Only the time-constrained problems with simple time constraints and simple time objectives represented in terms of time. This is a drawback of the approach.
Thank you.
Thank you.